In this example, a cantilevered beam will be modeled using the plane stress surface, using membrane elements. So the 3D structure will be modeled as a vertical plate parallel to the direction of the load. We are again choosing the same units as in the previous example: megapascal, kilonewton, millimeters. And we can start by specifying the property for a plate, and it is a 2D plane stress surface. Material is again steel, and the geometry, the thickness of the plate, vertical plate, is the width of the cross section of the beam, which is 50. Now we can create the nodes, and the first node is 0, 0. The second node is 0 horizontally, 100 vertically. Third is 1200 and 100. And the last one is 1200 and vertically 0. I can now redraw. So the 4 nodes exist there, and I will now create an element, quad 8 type. So it's a plate element with 8 nodes, using the plate property 1, which we have specified, and I'll click on all the 4 nodes. And to finish, I will click on the all. So that creates a single plate element with 8 nodes. Now I'm going to restrain the nodes on the left, so all are fixed, and I'll select all the nodes on the left hand side and apply. To apply the load, we can use the edge shear stress. So on the edge on the right side, and the direction of the stress is from lower to higher number node, so it is downwards, and it's equal to the load divided by the area of the cross section, which makes the stress of 2 megapascals. 10 kilonewtons divided by 50 times 100 area. Add. Now I can save this as case study 2 and solve it. I'll open the results file, and we need to calculate the vertical deflections. So to do that, to display the vertical deflection, I will use again the graph. And we need the vertical deflection on the nodes on the top surface, so on the top line of the beam. These are the values, slightly different than in the previous case study. So I can note them in the table for the element 1. The next value we need is the bending stress along the top line in the x direction. So in a similar way, I'm going to the graph option, new graph, and okay, now instead of using this we need a plate, because stress is related to the plate rather than to the beam, and we use global xx, create select the position, the top two nodes, and click OK, and this displays the stress in the x direction, average one, 81, ranging from 81 to 62, 81 on the left and 62 on the right, which is clearly not correct because here the stress should be 0. We are going to now display also, using the graph, the shear stress along the YZ. YZ is the line at mid-length of this beam. So we are looking at the plate property, global stress xy, which is the shear stress, and for the position, these two nodes only. In both points, the shear stress is minus 2 megapascals. Now I will close the results file, save this file, and then save it as case study 2. The next stage is to subdivide this plate into 2 plates, so I'll call it case study 2.2. We are using tools Subdivide, and click and see we need to subdivide along the B, so in the B direction it should be 2, and apply. So this has subdivided into 2 plates. Oh, sorry, undo. I haven't specified tools subdivide. I haven't specified the target should be quad 8, not quad 4. Right, so if I click on the beam, and we're subdivided in the B direction, and now we have 2 quad 8s. Save and solve. And if I open the results file, I can again display the graph of the deflection, dy, between the first and the last, which gives these data points. And similarly, I can display the graph of the stress in the xx direction, global, against the position from here to here, data points, considerably different than in the previous example, and the graph of shear stress, global xy against here, and it is still 2 megapascals. Having done that, I can close the result file, and I can now save this as 4 because I'm going to subdivide into 4. Tools, subdivide. And we again are subdividing in the B direction into 2, and the resulting target is code 8. So now there are 4 plates, and I can do the analysis again, and then I can subdivide each of these plates for the last to get 16 coordinates. At the moment we have this is 4 coordinates, 4 plates. Now I can subdivide each of these 4 into 2 along A now, and lastly I will subdivide again along A into 2, all of them, to get 16 coordinate elements. So doing the analysis in exactly the same way.